So now that we've covered the basic background of flash solid-state drive devices, next, let's look into the flash architecture, how it works internally, okay? So as we've already mentioned, a flash device is one of the electronic storage devices. So it holds charge at different levels to represent different data, different state that it tries to preserve, it tries to memorize. So there are multiple different kinds of technologies that supports this different level of charges per cell, right? The first kind of technique is called SLC, which is a short of a single level cell. So in this technique, each NAND cell is used to hold charge at two different levels, basically binary states. And if you take a look at this example, the Y dimension, it represents the charge level. And above the threshold, so there's a threshold in the middle. Okay, so below the threshold, it represents a state, and above the threshold, it represents a different state. Basically, you use these two different states to represent binary data, 0 and 1s. Okay, so above the surface, above the threshold, it represents a value of 1, and below the threshold, it represents a state of 0. So this is SLC. And a more denser technique is called MLC, which is a short of multi-level cell. Within multi-level cell, the fundamental difference against the single-level cell is that, as its name suggests, it holds multiple different levels instead of only one single level, right? Again, the Y dimension represents the charge levels. And the lowest level, it has 3 different thresholds, okay? 3 different levels. And the lowest level, if the charge level is below the lowest threshold, it can be used to represent a state of 0, 0. As you can see, it can be represent 2 bits. So each cell represents 2 bits, which means 4 states, okay? 0, 0, 0, 1, 1, 0, 1, 1, okay? These 4 different states. And if the level is above the lowest threshold but below the middle threshold, it represents 0, 1, okay? And so on and so forth. Above the middle level, it represents 1, 0, which is 2, right? If you above the level, the charge level is the highest, it represents the 4th state, which is 1, 1, which is 3, okay? So that each multi-level cell can be used to represent a total number of 4 states instead of only 2 binary states, which is supported by the single level cell. So the difference between these 2 different techniques is robustness, its ability to be, to be resilient against errors, and also the price. Okay, so single level cell, since it's more robust, and each and every cell can only be used to hold 2 different binary states, so it's relatively more expensive, but it comes with a more higher level of robustness, okay? Because each single cell can be used to hold only 1 single bit in 2 different states. In contrast, for MLC, multi-level cell technique, it's relatively cheaper, right? Why it's cheaper is because 1 single cell can be used to hold multiple bits. In this example, 2 bits or 4 different states. But it's kind of sensitive to the error. It's more prone to error because it is used to maintain 3 different levels and 4 different states. And the likelihood, the chances of getting an error is way much higher compared to the case on the left-hand side, which is the single level cell. Okay, so these are the trade-offs between these 2 different techniques. And both of these are used in, flash solid state drive devices. So since we've talked about this robustness or resilience to the errors, one fundamental issue that is being faced by this kind of electronic flash-based solid-state drive devices is these flash cells, no matter whether we're talking about single-level cell or multi-level cells, these cells, they could be worn out after being erased too many times. And recall that flash devices cannot support overwrite. It doesn't support no overwrite. If you want to overwrite, you want to write something to some place within the disk that has already been written data, you have to erase this whole flash block so that you can overwrite. Okay, so this erase operation, it impacts the lifespan, the lifetime of the flash device, because each cell could only be erased a limited amount of times. If you're talking about MLC, the lifespan is typically in the range of tens of thousands of times, right? So that is why it's less robust as compared to single level cell, which is at the range of hundreds of thousands of times, which is roughly 10 times better in terms of 10 times longer in terms of lifespan compared to multi-level cell. Okay, so whenever talking about this wear out, this flash-based lifespan or so-called endurance metric, what kind of technology could be used or strategy or policy could be used to maximize endurance? Okay. How to maximize endurance for a flash device? A typical technique is called wear leveling. So you can think of wear leveling as some sort of, write balancing technique. It tries to balance the writes among all the flash blocks, among all the flash pages, so that it avoids the likelihood that a single flash block or single flash page gets overwritten, gets erased too many times, so that only that particular single hotspot become bad or become error prone like way much sooner compared to the rest of the places, locations within the flash device. Okay, so basically this strategy is used to achieve the objective to prevent some cells from being worn out while the others are still fresh. Okay, wear leveling, or you can call it write balancing, or erasure or erase balancing kind of technique. So this is one technique that is used to maximize endurance metric for a typical flash device. So here, let's look into the flash internals and see how the architecture looks like at a very high level, abstract level. And recall that one of the primary performance benefits come from this inherent I/O parallelism. But how can a flash device support parallel I/Os? This is because a flash device can be divided into multiple flash banks, or in some other literature, it's also called flash planes, right? And these flash banks, in this example, it shows 4 flash banks. And these flash banks can be read in parallel, can be accessed in parallel, okay? As shown in this example, there are 2 concurrent read operations hitting on the first and the third flash banks, okay? And these 2 read operations can be serviced simultaneously or concurrently at the same time. So this is why it can achieve way much higher throughput and lower latency compared to the hard disk drive because the hard disk drive is inherently serial. It's not inherently parallel. So that means at any single point of time, only one outstanding I/O request can be serviced by a hard disk drive. Okay. So next, let's talk about flash write operations. How does flash support these various different write operations? First of all, at a very high level, it supports asymmetric writes. By asymmetric, I mean there are two different writes. The first one is the fine-grained write operation, okay, where the flash device write all zeros. This is relatively faster and relatively finer grained. And the second type of write operation is the more costly write operation. It is really slow, and the granularity is coarse, is bigger compared to the previous smaller write operations. And in this coarse grained write operations, instead of writing zeros, it write ones, meaning erase everything. So here, ones means the fresh state. Okay, so this is so if any place within the flash device, it stores ones, meaning that particular place is not being written with any new data. And it uses zeros to represent data, okay? So writing zeros is also called program. This writing zero operation is called fine-grained writing zeros operation called program. In contrast, this writing ones is called erase. Whenever you write ones, you write as coarse granularity, you erase basically all the data right into this particular flash block. Okay? And another important thing is the granularity where these two different kind of write operations happens. So the writing zero, the program operation happens at the fine-grained page level. And the erase coarse grained operation happens at the coarse grained block level. Okay. In the next couple of slides, we'll be talking about the difference between this page and the block terminology. So the third bullet shows the flash can only write or program into clean pages. By clean, I mean the page contains all ones. If the page contains like 1% ones instead of like some random zeros, meaning this page can have been erased. It starts off with a new fresh state. It can accept new write operations. But whenever there's some data or some zeros that has already been preserved in any one of these, flash pages, that particular block cannot be overwritten. Okay? So that particular flash page cannot be overwritten. You have to do a whole flash block erase before you can write anything new into that. Because flash doesn't inherently support in-place overwrite. Okay? So this is the most important that you need to know, you need to get a sense of in order to fully understand the fundamental differences between the mechanical hard disk against the electronic flash devices. And here, this example shows 4 different flash banks or 4 different flash planes. A typical flash bank can be further divided into multiple flash blocks. Okay? If you zoom into one particular flash block, it further contains multiple flash pages. And here, in this particular example, this flash block contains 8 pages. And recall that the flash page is a basic granularity of read and write for a flash device. Okay? Okay? But in terms of write operations, it's more trickier compared to the read operations because it supports 2 different writes and it doesn't support overwrites. Okay? Keep that in mind. So in this example, starting off, it starts from a fresh state. All pages are clean, meaning all pages are programmable or writable. At one point of time, there's an application. Write some new data into the flash, into this particular flash block. And this operation is called program operation by writing, zeros, okay? So these zeros all represents data from applications. Okay, at a later point of time, you write more data into a different, basically the sixth flash page within this particular flash block. And you also write zeros at different places to represent different state. Okay, so this is the second program or second fine-grained write operation. So at this point of time, because this particular flash block has already absorbed these two program operations, these two flash pages are now holding the data and thus cannot be overwritten, okay? If you want to still write something new into these two particular blue-colored, already dirty flash pages, you need to do a whole flash block erase operation. Okay, you want to still write new data to this page which has already been written, which is already dirty. Okay, dirty. So you need to erase this whole flash block. Okay, erase the whole block. By erasing, it basically flips all zeros into ones. Okay, and after erase, again, it holds all free state. It flips all the data, erase all the data away. So right now it can be accept a new program again. Program and program. Okay. So right now, again, there's a new program operations that hitting on the very first flash page within this particular flash block. Okay. So in this slide, it uses these four squares to kind of illustrate the differences in terms of interfaces or APIs between these two different storage technologies. So at the horizontal dimension, it shows two columns. The first one is disk, and the second one is flash. In the vertical dimension, it shows there's two different read and write operations. Read and write, okay? So in terms of hard disk drive, you read at the granularity of flash block or disk sector, okay? And similarly, in the context of a flash device, you read at the flash page granularity. And these two granularities are conceptually the same. Typically, the size of either sector or flash page is 4 KB. Okay? Okay, so this is read operations, but write operations are dramatically different. In the context of disk, it's simple. You just write sector, right? Either write single sector or multiple sectors. But in the context of flash device, it's different. As we've talked about this like multiple different times, again, note here, it supports asymmetric write operations, okay? Erase is at the coarse granularity, write all ones. And program is to write something new into this already erased data starting off from a fresh state. And you can only write something new into the fresh state flash page, which contains all ones. And program operation is to write zeros, flip ones back into zeros. So this is the program. operations. Okay, erase operations, flip all zeros back to ones. Erase operations. So, but how many flash blanks or flash planes in a typical flash device? We're looking at 1,000 or 4,000 flash blocks per flash bank. And banks can be accessed in parallel, can be read in parallel, okay? If you're talking about the flash block, it can hold from 64 to 256, these many fine-grained flash pages, depending on the granularity of the flash pages that get configured by the users, because the granularity of the flash pages is configurable. It also, importantly, the flash page is the fundamental unit of erase operations, okay? And the flash page, its size is from 2 to 8 kilobytes, and it's a unit of read in the program, fine-grained write operations. Okay, so this is why we're looking at these two different performance behaviors between these two fundamental different storage device technologies. Okay.